background of our project, the current works which are available in the market which involve fire is all done in non-real time. And it also uses 2D sprites in a 3D space, which means that they actually just superimpose the 2D sprites at a certain axis, and it looks real, but it's not actually a full fire physics. And for burning objects, basically current market technology available is predefined burn animation. So every object, each time it burns, it will only burn in that particular way. And also, when the object is burning, normally what they do is they replace one model with a burnt model, so it looks as though it's burning, but it's actually not a real-time burning. And there's no material deformation in the burning physics which is currently available. There are also no such things as wind elements involved, and there's also no soft body physics involved with burning physics in current technology, such as curling or crumpling, for example, when the paper burns. Our scheduled plan was during the first week, during our stage 1, what we actually did was we developed our sheet materials with particles, so each material will have different properties. We also define the interparticle interactions, so that once we start a fire at a heat point at a particular place, how it will interact with the other particles. So after accomplishing this in stage 1, our plan for stage 2 was to start having environmental effects such as wind. So if once the particle starts burning, and if a wind is blowing, how the fire spreads and how the ashes and the flames actually react. So after accomplishing this, we proceeded to our plan on stage 3, which was to have the visualization effects, such as, for example, this is a sheet metal. Once it starts burning, it becomes molten and also releases steam if there is moisture available. We will proceed to discuss what is fire. So as you can see, fire actually consists of 3 components: air, heat, and fuel. So we have incorporated this concept into our particle system. Our particles will consist of fuel, which is a material itself. Different material will burn in a different to a different extent. Of course, the heat, how much heat intensity and how it spreads, as well as if there's any external conditions such as moisture or oxygen or any wind factors. Alright, so this is basically the section on the mechanics that we have used, the physical laws that we have used in our particle system. So basically our entire solution is based on particle system. So some of the things which will come into play are things such as gravity. So these are basic Newtonian laws of velocity and position, how the particles will move and interact with gravity. And of course there's the spread of wind or the spread of fire, which is using this heat exchange times the wind vector. So if there's a wind, and depending on how much heat, there'll be a certain spread of heat. Of course, burning will depend on the material, how much fuel the material provides. So as the material burns, it will lose its fuel capacity, which we have incorporated into this formula. And of course, as each particle burns, it passes on the heat information to its neighboring particles. So in order to find out its neighbors, we are using this particular formula where as long as any particle is within a radius of this particular particle, it will be considered as a neighbor and will receive any heat information or any other particle information. This is fire mechanics. So basically the particle will burn depending on how much heat it has received, and we have multiplied with a random variable so that it will create a randomness to the way the material burns. And of course the particle will remain stationary for as long as it is below a count of 20 in our program. And of course the weak link will determine the minimum position at which the particle will stay alive. Then of course we have the velocity of the spread. So this again is we have created randomness into it so that it looks real when it is presented. And how the fire jumps, once again, if it's within the radius, it will hop on to the next particle and continue burning. So this particular fire mechanics is on the particle itself. Then we also have external factors such as wind. So wind is also subjected to Newtonian laws such as gravitational laws. So velocity and position will come into play again, and wind particles will follow in their own direction depending on the velocity and wind strength that we have set. And the wind fires will also follow the previous, but it is scaled down. This is the flame, which is our heating point, which we are incorporating, which we'll probably see later as green objects in the demo. They also follow the similar gravitational laws. Wind spread is none in this case because we are just throwing projectiles of heating elements onto the materials. So once again, when the flame particle reacts with our material particle, it will just spread the information to the neighbors as long as within the radius, same as in our previous particles. And of course, it will burn the neighbor which is defined as a neighbor of that particular position. Okay, so basically this is our system architecture in real time. We will have the XNA engine running on its own platform, and then we will have things such as a player actions, and mind you, this is all in real time, so all the camera movement controls, the shooting of the flames, the movement in and out of the screen, everything is in real time. And all our methods which I discussed earlier is also being run at real time at a frame rate of 60 Hz. There is a loading phase, but then again, as in any game, there's always a loading phase when you're playing the game. Our program data structure basically consists of arrays and not any other type such as linked list or anything. The reason we have used arrays is because we can pinpoint all the indices without having to search through. So this speeds up processing of the game. So this is our code overview. Because we are using particle systems, it is easy to convert each particular point into a vertex for easy shading or incorporating into a model. Most materials and properties which we have defined in our game constants, it makes it easy to use as a general class. So many different games can just use, and they just select whichever game constant they want, and they can just incorporate our solution into their games. And because it's an individual particle system, every particle behaving on its own is an independent subsystem. It can be modified without affecting other systems. Alright, as in any system, there's always advantages and disadvantages. Advantages for our system is it is fast because it's running real time. We are using a data structure which is easier to work with. It's a very modular system. We can change things without affecting other aspects of the solution. It's easy customizable, which I've just explained, like points being converted to vertices, and it is realistic, as you will soon see once we have put in the visualization. And we have also done a lot of intensive research, as you can see from our list of references.